Welcome to the recent Advances in Biomedical Engineering sector seminar, organized jointly by the Chamber of Electronical Engineers and Cyprus International University Biomedical Engineering Department. I would like to invite the Dean of Faculty of Engineering, Professor Dr. Serkan Abbasoglu, to the stage for his speech.
Mühendislik Doğa Birliği Başkanım, çok zormuş ama. Onun sergisi oldu.
Elektrik Mühendisliği Odası Başkanım, değerli konuşmacılar, sayın meslektaşlarım, değerli arkadaşlar. Dün akşam bir ilk kez denedim Sayın Başkanım. Gerçekten sakin söylemek lazımmış. Onur Kurulu üyesiyim ben şu anda Kıbrıs Türk Mühendis Mimar Odalar Birliği'nin uzun süredir de içerisindeyim. Dolayısıyla yani özel bir bağım var. Bu arada Uğur Bey de aynı zamanda Kıbrıs, Türkiye Mühendis Mimar Odalar Birliği EMO Yönetim Kurulu üyesi. Hoş geldiniz tekrardan. Diğer arkadaşlarımıza tekrardan hoş geldiniz. Bugün aslında çok önemli bir etkinlikte beraberiz. Biyomedikal bizim için yeni bir mücadele diyelim. Aslında bu iki tane çok önemli, belki ikiden de fazla aslında çok multidisipliner alanların bir araya geldiği özel bir bilim alanı. Mühendisliğin o problem çözme, analitik düşünme yeteneklerinin sağlık bilimleriyle, tıpla bütünleştiği bir bilimden bahsediyoruz. Yani bence çok heyecan verici. Hem geleneksel mühendislik hem de günümüzde artık yapay zeka gibi, robotics gibi güncel veya top-end dediğimiz teknolojik gelişmelerin bir araya gelmesi ve bunu sağlık bilimleriyle buluşturmak, tabii Mustafa Camgöz hocamız da burada, bizim özel çalıştığımız alanlar olduğu için gerçekten heyecan verici. Bizim fakültemiz adına bir iki cümle söylemek istiyorum. Mühendislik Fakültesi şu anda en büyük fakültelerinden biri üniversitenin. 2700'e aşkın öğrencimiz var. Bunların 2300'e yakını lisans, geriye kalanlar yüksek lisans doktora öğrencileri. 38 programımız var. 18 lisans, geriye kalan 13'ü yüksek lisans, 7 doktora programımız var. Yani çok aslında farklı alanlara, farklı disiplinlere çalışan büyük bir fakülteyiz. Birçok akreditasyonumuz var, ulusal, uluslararası. Bu çerçevede büyüyen bizim aslında parlayan yıldızlarımızdan biri biyomedikal mühendisliği. Yaptığımız çalışmalarda özellikle bu noktada Ali Işın Hoca'ya da özel bir teşekkür etmek istiyorum. Yani hem Sağlık Bakanlığı tarafından bu yolu yürürken bizlere destek veriyor, rotamızı çizerken. Bölüm başkanımıza da aynı şekilde teşekkür etmek istiyorum. Çok önemli bir alanda ciddi çalışmalar yapıyoruz ve ben bugünkü toplantının da sadece öğrencilerimize değil bizlere de yol çizeceği inancındayım. Yapacağımız bundan sonraki bilimsel ve eğitim faaliyetleriyle ilgili. Bu noktada biliyorsunuz biyomedikal mühendisliği elektrik mühendisleri odasıyla mesleki faaliyetlerini koordine ediyor. Elektrik mühendisleri odamızda bu etkinlikle ilgili ilk görüşmeyi yaptığımızda aslında cümlemi tamamlamadan tabii ki de Sayın Başkan'a etkinliğin bütün sorumluluğunu alan, birçok faaliyeti gerçekleştiren Çizgi Hanım'a özel teşekkürlerimi sunmak isterim. İbrahim Bey'e özel teşekkürlerimi sunmak isterim. Yani bundan sonra daha yakın temas ederek yani bu alanın öne çıkmasını aslında sağlamamız gerekiyor. Çünkü ihtiyaçtan aslında önümüze gelen bir disiplin. Dediğim gibi tüm katılımcılara başarılar diliyorum. Teşekkür ediyorum. Müsaadenizle bir iki cümle de yabancı öğrencilerimize söylemek istiyorum. Dear students, dear guests, I would like to welcome all of you to this valuable organization event. We believe in that biomedical engineering is one of the future professions and it's important and valuable part of our engineering faculty. It's a new department when you look at the age of the biomedical engineering, but with our experienced staff and infrastructure, valuable infrastructure, I believe in that in short period of time we will have great success in the field. You know, biomedical engineering is a multidisciplinary field where we are trying to solve health, medicine problems or sciences, join the medical sciences with engineering. And I believe in that this meeting will be a nice roadmap and guideline for our future studies in coordination with Chamber of Electrical Engineers. So I would like to welcome all of you. Thank you very much for your contributions.
Now I would like to invite the President of the Turkish Cypriot Chamber of Architects and Engineers, Mr. Tunç Adaner, to the stage for his speech.
Serkan Hocam gözlükler burada kaldı. Öncelikle değerli misafirler, hocalarım, onur kurulu üyem, oda başkanım ve yöneticilerim ve uzmanlarımız. Açıkçası samimi bir ortam olmasının sebebi ki bizim çok önem verdiğimiz bir durumdur. Üniversitelerle birlik ve odaların işbirliği her zaman için bizde öncelikli bir politikadır. Bu tabii ki şunu getirir. Sizler gibi öğrencilerin eğitim sürecinde, akademide hocalarımızdan eğitimleri alırken, hocalarımızın odalarla olan ilişkileri, odaların meslek hayatında, serbest meslekte veya uygulamadaki tecrübelerin, bunların her birinin birleşerek doğru bir şekilde öğrencilere aktarılması, sizlerin ileride meslek hayatına adım atarken iyi yetişmiş bireyler olarak bu yolda yürümeniz için önemli bir katkıdır. O yüzden biz birlik ve odalar olarak bu yönde her zaman için akademide olan hocalarımız olsun, üniversitelerle ilişkilerimizi hep geliştirmeye, hep üst düzeyde tutmaya çalışırız. Burada açıkçası şöyle bir şeye daha değinmek isterim. Biz birlik olarak Kıbrıs Türk Mühendis Mimar Odalar Birliği 15 odadan mevcuttur ve 5000'e yakın üyemiz vardır. Ve şu anda Kuzey Kıbrıs Türk Cumhuriyeti'nde en büyük, en geniş üye katılımına sahip sivil toplum örgütüyüz. Yarı kamu halindeyiz. Yasayla kuruluyuz. Bunun özeline indiğimde bugünkü seminerle ilgili olarak özellikle Elektrik Mühendisleri Odası Başkanlığı Yönetim Kurulu'na gerçekten teşekkür ederim. Teşekkür etmemin bir diğer sebebi de şudur. Biyoteknikal konusunda uzman olan mühendis arkadaşlarımızın örgütlenme adına, çünkü bizde 15 odaların belli bir özelliği vardır her bir meslek grubuna göre. Fakat farklı meslek grupları oluşabilecek veya eğitim almış kişiler, uzmanlar geldiği zaman örgütlü mesleklerinde örgütlü davranmak istediklerinde birliğe ve odalara kayıt oluyor. Burada o oda hangi odaya daha yakınsa meslek örgütü onun altında mesleğini icra etmeye veya örgütlenmeye veya sivil toplum örgütü halinde topluma ve kamuya hizmet vermesi için fırsat tanınmaktadır. Yani birliğin 62 yıllık geçmişindeki en büyük felsefesi ve amacı bu tip meslek örgütlerinin, meslek uzmanlarının toplum içerisinde örgütlü olarak, birlik olarak seslerini çıkarabilmelerini, doğruyu söyleyebilmeleri ve gerçekleri anlatabilmeleridir. O yüzden biyomedikal mühendisler arkadaşlarla daha önce de toplantı yapmıştık. Elektrik Mühendisliği Odası altında şu anda görev alıyorlar ve Elektrik Mühendisliği Odası Yönetim Kurulu da onlarla ilişkilerini çok iyi tutuyor. Bundan dolayı bu karşılıklı ilişki bizim için de çok sevindirici. Bundan dolayı tekrar tebrik etmek isterim. Bugünkü seminerin sonuçta biyomedikal dünyada en önemli sektör, sağlık sektörü ve bu sağlık sektörünün gelişimi özellikle teknolojik sistemlerle ilgili, cihazlarla ilgili çok hızlı bir şekilde gelişmektedir. Nanoteknoloji de bunlardan en önemli kısımlarından biridir. Ve bu konudaki uzmanlarımız, ülkemiz özeline indiğimizde durum biraz farklı olsa da dünya genelinde çok değerli uzmanlar ve açıkçası sektörün gelişmekte olduğu bir kısımdır. Ve bu konuda özellikle üniversitelere uzman yetiştirme konusunda çok daha fazla görev düşmektedir. Bizim ülkemize döndüğümüzde kamuda ve özelde çalışan mühendislerimiz vardır. Bunların ülkemizdeki sağlık sektöründeki sıkıntılara rağmen, teknolojik sistemlerin yetersizliğine rağmen en üst düzeyde yeni teknolojiyi takip edip de kamudaki veya özel sektördeki sağlık sektörüne katkı yapmak için ellerinden geleni yaptıklarını takip ediyorum, biliyorum, birey olarak da tanıyorum. O yüzden bu seminerin sonucunda gerek yurt dışından gelen misafirlerimizin ve bu konudaki uzmanların yapacağı açıklamalar ve bilgilendirmeler bizim için çok önemlidir. Ülkemizdeki sağlık sektörünün ve bu teknolojinin gelişmesiyle ilgili bize çok büyük katkı sağlayacağını düşünüyorum. Seminerin hepimizin adına başarılı geçmesini diliyorum. Teşekkürler.
Thank you. The section will start with the first presentation. I would like to invite Serkan Uğur Bayraktar for his speech about medical technology and industrial risk in health services with brief information about his background. Serkan Uğur Bayraktar graduated from Istanbul University Electronic Engineering Department and completed master's degree at Boğaziçi University Biomedical Engineering Institute. He is now at the thesis stage of Biomedical Engineering Doctorate Program at Erciyes University. He has written medical device management section in the book Hospital Management. Please welcome him.
Öncelikle ben de çok teşekkür ediyorum bu nazik davetiniz için. Benim için çok çok heyecan verici. Umarım yararlı olur. Heyecanımı, derdimi bir kısımda olsa paylaşabilirim. İngilizce devam ediyorum. Thank you very much. Good morning, ladies and gentlemen. I'm Uğur Bayraktar. Since 2000, I have been studying and working in biomedical sector, and since from the very beginning, my first anxiety is the industrial risks in healthcare sector, because when I was first realizing that the hospitals are full of technological instruments, infrastructure or whatever, and these technologies are not simple devices, etc. The technologies in a standard hospital, you can find all of them in any of industrial branches, any of. They are just focused in a building called hospital, and we have lots of people from newborns, childs, or very elderly old people. So I have started with American Hospital in Istanbul just after my electronics engineering graduation, and now I have a company. We called it Primum non nocere because it is the most important statement of my career. You all know Hippocrates. Primum non nocere means first do not harm. It's said to be the phrase belongs to Hippocrates. It's not important, but first do not harm is the most important rule of modern medicine. First do not harm. So we called our company First Do Not Harm. So biomedical engineering, when I was studying my final project in the electronics engineering faculty, my professor asked me, do you know what biomedical is? I couldn't answer, and now I can. Biomedical means something about biology and or medicine only. If you call biomedical engineering, then you are trying to develop some new techniques or solve some problems with engineering instruments or algorithms. And biomedical engineering is a huge parenthesis, which a little one is clinical engineering, and clinical engineering tries to manage the medical technology in a healthcare facility. A single physician room or a big city hospital, whatever, clinical engineers try to discipline and manage the healthcare technology. And this is a statement which I love. Clinical engineers try to translate and integrate clinical, administrative, and technical issues in a hospital. So, before 30 years, 35 years, 20 years old, silence was the biggest priority in the hospitals. We have this lady in all kind of healthcare facilities in Turkey. That's why in Turkish cinema, when you see this lady, you know that the main girl or main boy has a very serious medical process, and we hope he or she will survive. Only this image could provide this understanding. But now, everything has changed. We have lots of warning signs about technology in a healthcare facility. Electricity, for example. Yes, we have electricity everywhere. The most horrific scenario of a modern healthcare building is lack of electricity. When it's blackout, everything stops. During fights, earthquakes, or any other disasters, lack of electricity is the major problem because everything stops without electricity. But not as a supply, only not as a supply. For example, we will come back to that issue, but for a leakage current, not in milliamperes, in microamperes, you can kill a patient. And while only having an ordinary ECG scan exam, you can kill a patient with a leakage current in microamperes. So that's why it's a huge risk. And electromagnetic interference. When the cellular phones become more and more popular, our days went by deciding where to put this cellular phone in intensive care unit or in operating room. Will it be allowed or not? It was a big problem. Now it's okay, but not only the cellular phone. For example, you are trying to catch the electrical activity in your brain during a outpatient exam or in the operating room during a surgery. You are trying to reach the electrical signals. If you have an electromagnetic interference, all the signals are not suitable to study. So, strong magnetic field. I don't know any other industrial branch that have such a priority. But in a standard hospital, we have a device called magnetic resonance. And that magnetic resonance can kill people. In many sesimiz yok tabii. Okay, it's a huge magnet. The electromagnetic magnetic resonance device is a huge magnet, and you can't turn it off in any case. If an ferromagnet object is in the room too close to the magnet, then it will fly into the magnet and kill a patient or at least destroy the system. In the Bosphorus University, the first lesson of electromagnetic magnetic resonance system was about a 7-year-old girl was killed by a fire extinguisher, and this here will come a similar story in 2001, I think, I don't remember. But in 1985, a 7-year-old girl was killed in United Kingdom. The system was very big at that time, and there was a big technical room behind the gantry. So the technician saw that smoke coming out technical room. So there's a fire, girl in the magnet, and he has a fire extinguisher just behind. Catch it, go in, and fire extinguisher flies and kill the girl. And here, another version repeats in 2001. Not necessary to kill a patient, you can harm the device with uncontrolled materials in. They will be very happy when they solve the problem with these bulbs and wooden sticks, whatever, because they have saved just about 80,000 euros, avoiding to call for service from the manufacturer. So another problem about magnetic resonance to provide superconductive media in the magnet, we must cool it down and cool up to minus 270 degrees Celsius. So this is just little bit above absolute zero. The helium provides such cooling. So we have lots of helium gas in the magnet. In case of any leakage in the room, this amount of helium will go out. And if you cannot exhaust this helium out the room, out the building, it will take the place of oxygen and you can breathe helium. And the patient or the technicians in the room will die if this leakage happens in a closed room. So we have this device in almost every hospital. It's not a rare or hard to reach technology. So X-ray and gamma radiation, maybe they are the most simplest phenomena now, because any medical exam without medical imaging is not possible in Turkey. So medical imaging is indispensable, but of course provides ionizing radiation. And now not only single tomography or X-ray device, now we are trying to, we have cyclotrons, particle accelerators, whatever. Yani, these are atomic bomb developing techniques. Okay, compressed gas is another problem or capability. First of all, regardless of their content, if you have a compressed gas in a cylinder, in a bottle, it's a missile. Because the weakest point is the valve, the screwed valve, and with a simple impact, it can break and the cylinder may rocket. It can fly like a missile that pierces through the walls, even the walls. So, regardless of the content, oxygen, carbon dioxide, whatever, even compressed air is a great risk. But if you speak about pure oxygen or oxygen-enriched atmosphere, then fire phenomena change. Let's see. Do we have smokers here? No? Okay. It's how a cigarette smokes in normal conditions. if you supply oxygen, then everything changes. So, yeah, this is not valid in only experiments. Of course, this is valid in real life. And you may remember Baghdad hospital fire. 82 people were dead just because of oxygen-enriched media. Now, we have an oxygen leakage, probably. Lots of oxygen spilling out in the room. And there's a fire, and that fire goes very, very quickly, much quicker than we all know. And at the end, it is uncontrollable, and 82 people were dead. So this is the result, always this is the result when you can't control the technological risk in any media, but especially in hospitals. So laser is a very popular capability, but how is it possible to shoot directly into the eye with ophthalmic lasers where you can get blind with an ordinary laser pointer? We say that please do not direct your laser pointer to anyone because it can cause blindness. But in hospital, we directly shoot in the eye. Directly shoot in the eye. Because laser is a very complex topic. Every laser has a unique penetration in every different media. So every laser has a special protective glasses. One does not fit all. So nurses doesn't have this bubble in their mind. When they have a laser protective glasses, they put and go. You must check if this glass protect me from this kind of laser. So biological hazard, hospitals itself is a biological hazard source. But you must keep in mind that you can get HIV positive just from the cautery smoke inhalation in the operating room. That smoke, that cautery smoke, electrosurgical unit smoke, can carry HIV viruses. And when you inhale it, you have HIV positive, maybe. So, chemical risk, we use lots of chemicals in every area of healthcare processes. For example, ethylene oxide was very common for sterilization. And ethylene oxide is incredibly poisonous, flammable, really flammable, a big risk to have it in facility. You may remember the Beirut explosion. With ethylene oxide, you can experience something like that in your hospital. So, and too hot and too cold. Yes, we have lots of processes using very hot surfaces, very hot air, or too cold, very cold air. But too hot doesn't mean hundreds of degrees Celsius. For example, in one of the forensic cases where I worked as a specialist, a 7-day-old newborn baby has lost her nose and sense of smell because of a heated humidifier. The thermocouples, the sensors, heat sensors, were out of order somehow, and the baby inhaled humidified air at 75 degrees Celsius for about 45 minutes, and the nose was burned. And now they have plastic surgery has made a nose here, but she will not able to smell during whole life. So too hot doesn't mean hundreds of degrees. 50 degrees may be too hot. So electrical safety you may all know, of course, but during our normal life in our homes, offices, microshock, if we experience electricity flooding our body, yes, it's dangerous. But if you don't have a skin barrier, because our skin is a very good barrier for electricity, if you don't have a skin barrier, as I have mentioned at the beginning, because of microshock, if you don't have a skin barrier, current of milliamperes, even microamperes, flooding over your heart can cause death. So, and we have lots of instruments or devices providing an invasive electrical path. Not only the copper wires, for example, a invasive IV tube can provide the electrical path, and we have lots of them. So, in a meeting, this question was asked: what do you think? What is the most dangerous cargo in maritime transport? Most dangerous cargo. It may be chemical, nuclear, bulk cargo, container, ro-ro, military weapons. What is the most dangerous? Which one is the most dangerous? None. Human. Human transportation is the most dangerous maritime activity, because you can't control all human. Even a toy gun can cause a disaster in a cruise ship. So, human effect is the biggest problem in a hospital, because in a hospital we have lots of industrial risks with babies trying to walk, or a patient relative has just lost his or her loving, very agitated, or mental patients with mental problem, whatever. Patients with gun on their belt, and when they go into the MR room, the gun will splash into the MR room. The human effect, all these industrial risks, having them with lots of crowd in the hospital is a major problem. And now, cybersecurity. Because of digital medicine, we think, but every single simple hospital is a data center. We must provide the security of that data for the healthcare processes itself, and for even political issues. For example, if you can manipulate Mr. Putin's, Mr. Biden's, or Mr. Xi Jinping's medical records, we can cause a political problem. Yeah, that's it. Thank you very much.
We thank Mr. Serkan Bayraktar for his speech. Now we will continue with Ms. Eldem Albayrak. I would like to invite her for her speech about fish fluorescent in situ hybridization technical analysis and give a brief information about her. Eldem Albayrak successfully graduated from the University of San Diego in 2002, majoring in cell and molecular biology. Following her graduation, she graduated in molecular biology and genetics. She worked as a molecular biologist at the DNA laboratory of Dr. Burhan Nalbantoğlu State Hospital. She has been working as the head of DNA laboratory of Dr. Burhan Nalbantoğlu State Hospital since 2018.
My topic today will be a little bit different, so I'll take you to the molecular level of life and take you to the into the laboratory. Well, hello and welcome. And my name is Eldam Albayrak. I'm the head of the genetics laboratory in Dr. Burhan Nalbantoğlu State Hospital. I have been working there for 15 years now. And I am very honored to be here, and I would like to thank the Chamber of Electrical Engineers and the Cyprus International University for inviting me here for this presentation. And I would like to welcome you all and thank you for participating. My today's topic will be all about fish technique that's been recently has been started to be studied in our laboratory with the installation of a fluorescent microscope. So what is FISH? FISH is the acronyms for fluorescent in situ hybridization. So fluorescent, as you may all know, is fluorescent. In situ means in place, on site, in the position, so wherever the event is taking place. And hybridization is basically a fancy word for attach. So it's a molecular cytogenetic technique that's been used since the 1980s, and it's to detect the chromosomal abnormalities. So what it happens is you target a specific region on a chromosome, and with the use of fluorescent labeled probes, you can detect it. You can detect it with the probes I will be telling you about later. In the following slides, you will more about it, and you will hear more about it. So you detect the you basically target a specific region on a chromosome. So with the resulting in a colored signals that can be detected by fluorescent microscope. So before I actually go into more in detail about fish technique, I would like to go back to molecular cell and molecular biology 101 and explain a little bit about the structures of DNA and chromosomes. I do apologize to get out of the topic, but you kind of have to know about this for you to understand the technique itself. So please bear with me if you already, I don't really know the background of the people here in the audience, so please bear with me if you already know about this for the couple of slides. So, there are cells in your body. There are 37 trillion cells in your body, and each cell has 23 pairs of chromosomes. That means you have 46 in total chromosomes in each of your cell. So each cell, the chromosomes are thread-like structures that is, it's made of a long strands of DNA. So in order for it to be able to fit in the little nucleus of the cell, DNA has to coil around histone proteins so it can form a condensed form into chromosomes, so that it could fit in a little structures like nucleus, which is like 2 micrometer in diameter. If you think about this, geometrically it's equivalent to fitting like 24 kilometers of a rope into a tennis ball. So this is like an amazing molecular biology. That's what happens in your body, and that's totally out of our topic though. So I will continue with the DNA. So DNA is a double helix structure, and it's made of 4 nucleotides. It's GCAD, guanine, cytosine, adenine, and thymine. Guanine base pair with the cytosine, adenine base pair with the thymine. This is the basic principle of base pairing, which is when 2 complementary sequences find each other, they attach to each other, they hybridize together. So this is the basic principle of fish technique that you will hear a lot in this presentation. So you kind of have to understand the space pairing, so how they hybridize together when they find each other. So couple of terms about the chromosomes, about the structure of the chromosomes, so that you will again come up with in the later slides. So chromosomes, they have a short arm, P arm, and a longer arm, Q arm. And when in DNA replication cell cycle, DNA replicates and it forms the sister chromatids, the identical copies of chromosomes. So they are joined in the centromeric region. So, and the telomeres are the parts that protects the chromosome from damage. So telomeres are like the tips of the shoelace that you have, so it protects it from unraveling the tip of the shoe. So the telomeric parts are basically to protect the chromosome from damaging. So as I said before, DNA is all packed into chromosomes. So FISH technique is to detect the chromosomal abnormalities, and these abnormalities could be numerical and structural. So the chromosomal abnormalities can be, as I said, can be numerical and structural. So what numerical? It could be aneuploidies or polyploidies. And in aneuploidy, probably everybody knows here, I can give you an example of trisomy of 21. That's a Down syndrome, where there is a gain or a loss in a chromosome number. You have the aneuploidies, and Down syndrome is a good example where there is 3 copies of chromosome 21 in your cell, and polyploidies where you can have the triple in each chromosome. You can have 3 or 4 different types of chromosomes. So structural differences are, it could be deletion, where a segment of a chromosome is all deleted. It could be a duplication, where it's actually the part of a chromosome, it's duplicated. And it can be insertion from one chromosome to another chromosome. A part of a chromosome is actually inserted to the other one. And inversion is where it actually it turns upside down, and translocation is where 2 chromosomes swap parts together from each other. So it could be isochromosomes, where the P arms and the Q arms actually forms a totally different chromosome structure, and ring chromosomes actually lose the telomeric from the telomeric part. It loses. There's a deletion, so actually they come together and they form a ring structure, and that could be another type of an abnormalities that can cause disease that we look in FISH studies. So I said before that FISH is molecular cytogenetic technique. So what cytogenetic? Cytogenetic is to study of chromosomes, and of course there are advantages to it. The conventional cytogenetics actually is you can see all chromosomes together. You can see up top of the picture that you could see all 23 pairs of your chromosomes together, all karyotyped. So you can tell if there is any type of any differences. You can tell if there is any numerical changes. You can tell if there's any translocations or duplications. And you can actually visualize that in all karyotype. And of course, there are advantages to that you can screen for unknown defects, because you don't have to target any type of a disease. So you can look the whole picture. However, there are disadvantages to that you need fresh samples to do it, and you need cells to be in a dividing stage where you have to work with the metaphase cells, where the chromosomes are most condensed form in metaphase stage. So you have to actually wait for the chromosomes to get to that point, so to divide and to get, and this is like taking for 5 days to actually get to this point. So this is kind of a disadvantage to it, and that there's it's low sensitivity and low resolution, and it's totally reliable on a technician experience to analyze the karyotype, because as you see here, they're all lined up together nicely, but in the beginning, it was like all smashed up and all over the places, so you have to, based on their centromeric position, bonding places and bonding structures and the size, you have to actually line them up, like this is chromosome 1, this is from chromosome 21, this is 19. You have to all lined up like a puzzle to put them together. So it's kind of, it's taking time and analyzing it. It's very reliable to the experience. So molecular cytogenetic, on the other hand, FISH technique is much easier. It's a simpler and it's a faster technique, and it has high sensitivity and high resolution, and no metaphase cells are needed. You can work with the metaphase cells, of course, and sometimes you have to, I mean you do, but mostly interphase cells are used, so you don't need to wait for 5 days. You can actually, it takes the most 2 days, and sometimes you can end the experiment in 1 day. So, but the disadvantages, you have to target the regions. So you can work only with the targeted region. So you have to know beforehand what the disease is and what you're looking for on the chromosome. So there are specific probes that I will tell you about later, that they're made to that specific region. So you can only use that in FISH studies. And there are, of course, the disadvantages. There are limited probes and available in the market. So what's principle of FISH? Again, there is your DNA. That's your target DNA, where the DNA that you want to look if there is any type of a chromosomal abnormalities. And there's your probe DNA. The probes are a little segments of DNA that is fluorescently labeled, that is complementary to your DNA, and they will come together, attach together, and under the microscope, they will, after hybridization under microscope, you will see signals, colored signals under the microscope, and you can detect them under the microscope. So, so what is probe? Probe is, again, it's a complementary sequences of target nucleic acids. They are designed to sequence of interest, and they are fluorescently labeled, and the size can range from 20 to 300 base pairs. As you see on the top left picture, it comes in a little tube, and you just use like 2 to 10 microliters of that tube only for the probe. So what type of probes that we use? We use like whole chromosome painting probes, where the whole chromosomes are painted. You can analyze the whole chromosome. It could be centromeric region probes, where the centromeres or telomeric regions of the chromosomes are labeled. You can use a locus-specific probes with they are the gene-specific, so you have to target a specific part, specific gene, when you use the locus-specific probes. And so what we do in the laboratory, getting into a wet lab, so we have to prepare the cells first. So how do we do this? Well, we actually treat it with the hypotonics, so cells are swelled up like a balloon, that it actually, when you put them on a slide, they will burst, so they can get the probe in, and then DNA can attach to the probe. So what happens is, think like a balloon fill up water, then you actually throw it, and then it bursts. It's just like that. This just what happens here. You actually put it on a slide. You fix it with a fixative on a slide. So you spread the cells, you fix it on a slide, so then you have to denature your DNA. So your target DNA, you have to denature. So in order for you to denature this, you have to heat it up. So on a heat block, you increase the temperature, you heat, you denature your DNA, and then the probe is fluorescently labeled already, so you actually hybridize with the cooling. You hybridize them together overnight in the hybridization that goes for overnight, and after 1 day in the hybridization chamber, you can do the post-hybridization washes where you actually clean up the all unbound probes and other stuff, and then you counter stain. And to do that, we use DAPI. It's a nuclear stain that stains the nucleus, so the vivid colors of probes, like the red and the yellow and green, can actually stand out in a blue background. So then we put them on a microscope, and the microscope actually captures the images, and we go and start analyzing the cells and what's happening there. So what type of sample types we get? We get peripheral blood, we get bone marrow that's taken from the bone behind your back, cord blood, amniotic fluid, and chorionic villus sampling. The last two is taken from a pregnant woman in their pregnancies. Said that, well, this slide I won't get into detail. I don't want to get into detail because the presentation after me by Dr. Alp Eidos, he is the one who actually set up the fluorescent microscope in our laboratory that we love so far, too much. So he will actually give you a much better detailed information about the microscope itself, but this is our fluorescent microscope that we do the fish analysis with. So diagnostic application of fish. So we use it for prenatal diagnosis. What I told you about before about the amniotic fluid, we get amniotic fluid or the CVS samples from a pregnancy. So we get them into the laboratory, so we can use fish analysis to see if there's any chromosomal abnormalities on the baby that the mother carries, or you can actually do PGD analysis as well, where it's
prenatal genetic diagnosis. You can do analysis on the embryos before implantation. So you can tell which embryo you want to implant into the, and go on with the IVF cycle. So you can, as I told you before, you can use it for the identification of the chromosomal abnormalities. You can monitor the success of bone marrow transplantation. Well, you can do chimerism analysis where you can see the percentage of X and Y, and then to see if the bone marrow transplantation has been successful. And you can monitor the disease progression in cancer, which I will give you an example later on this presentation. And you can characterize the marker chromosomes. That's like the extra pieces hanging around. So those sometimes could cause disease. So you can characterize those. And congenital abnormalities, as I told you before, trisomies. Trisomy 13 is the Pateu disease syndrome. 18 is the Edwards syndrome. 21, trisomy 21 is the Down syndrome. And you can have the XY aneuploidies where you can have, instead of 2X, you can have 1X in a female. And that's a Turner syndrome. And you can have 2X and a Y. That's a numerical changes again. You can have 2X and a Y, and that's like a Klinefelter syndrome. Or you can have triple X, and that's like a super female syndrome, it's known, and so on. And you can have microdeletion syndromes, such as
Krichuchat. That's actually a very interesting disease where it's known it's characterized by a cat meowing. So the children with this disease, when they cry, they sound like a cat when they cry, and that's caused by a deletion on the P arm on chromosome number 5. And Prader-Willi and Angelman, it's another microdeletion syndromes where it's caused by a deletion on 15 on the Q arm of the chromosome. So this is a clinical example of a DiGeorge syndrome. That's a deletion on the 22Q arm of the chromosome. This is not an example from our laboratory. This is just an example to actually give you to understand what's going on, what we do with the fish. So this is a DiGeorge syndrome. So that's an inherited immunodeficiency syndrome. It's caused by a deletion on the chromosome 22. And that's known to be a most common microdeletion. It's characterized by clinical features catch-22, where most of the people with DiGeorge syndrome have cardiac disease, and they have a specific facial features where they have the wide-set eyes, low-set ears, undeveloped chin, small upper lip, and the hooded eyelids. And they mostly, they have an absence in the thymus, where the T cell production that causes the T cell production abnormality. And they have this specific feature of cleft palate that's like a split in the roof of the mouth. And so they have a problem with the speech and with swallowing. And hypocalcemia is like where they don't have enough calcium in their body. But that's, anyway, this is like the clinical part of the syndrome. And as you see on the top right, there's a missing deletion on the Q arm of the chromosome 22. So what we do is it comes to our laboratory. So we have a probe that is specific to DiGeorge. So and what you see here is 2 red dots and 2 green dots. Greens are just for a control probe. If actually the assay has been worked, we check. So you see here that 2 red dots on the right picture is missing. So that means there is a deletion, and the probe actually couldn't go and hybridize with the DNA. So that's why we're missing the 2 red dots here, that the hybridization actually doesn't take place. So that's why we're missing. Of course, we do this, you see 1 cell here, but we do this for 200 cells to actually finalize that this person has the DiGeorge syndrome. You do this for around 200 cells, and you have to analyze and decide if, and this is sometimes the pictures are not this clear. You have to decide if there is a spot there or if there is not spot there. So it has to, in order for you to report it, it has to be above a threshold line and threshold limit that you have to, if it's okay to be reported. So that's an example in a chronic myeloid leukemia. That's a cancer. It's a leukemia, and that is caused by chromosome number 9 and chromosome number 22. Actually, parts of the chromosome 9 and chromosome 22 is coming together and actually making a totally new chromosome called Philadelphia chromosome. So here what you see is a fusion gene, a fusion chromosome where the BCR is shown on the green spot and ABL is the red. So when they come together, they make orange color. So you can actually analyze with the orange color being the presence of the Philadelphia chromosome in the cells. And again, so if you have this type of a chromosome, it's an uncontrolled cell. Your body actually uncontrolled cell production makes uncontrolled cell production. So we do this, and of course, you can actually see the progression on the disease because you check the 200 cells, 300 cells, whatever, and then you can actually see the progression if the percentage of this chromosome, the Philadelphia chromosome, actually decreased or increased after they get the treatment. So we can, this is how they prognose to see the progression on the disease. So this is the Down syndrome. So we have actually opened up 2 weeks ago, and this is our first patient in the laboratory. So we diagnose this as Down syndrome. So here you see in the Down syndrome, as I told you before, it's a trisomy of 21. So you see the red spots are the trisomies. So you have 3 chromosome 21 here, and we actually confirmed it with the karyotype on the right side. That's the conventional cytogenetics. And as you clearly see, there's a numerical changes on 21 that you have 3 chromosomes on 21. So we basically confirmed it with this. And this is our cytogenetics laboratory. This is the scenes from our wet laboratory. This is our microscope in the middle. This is our brilliant microscope that I really do want to take it home sometimes or sleep with it in the laboratory sometimes. This is very, very important to us. And actually, before I end up my presentation, I would like to point out how important actually this type of genetic testing for diagnosis, because people can go undiagnosed for years and years sometimes, and that's very frustrating for families, frustrating for children. And with the right diagnosis, you can get the right treatment so that the lifespan of those people with the disease can get longer, or you can ease the symptoms at least what they have, and they get a better life because of they have been diagnosed and they know what type of medicine to use. So this is very important, and I am very grateful to be able to start this in our laboratory and offer this type of testing to our community, to our families, to our children, to our hospitals, doctors, and to you. And I'm very happy about this, and I would like to to set that, I would really like to express my great appreciation to Ali Ushan. He has been there for us all the time from start to end. He has been there. He has supported us all the way through from the buying process of this microscopy, and I am very grateful to have someone in our ministry with that wide of vision that could understand the importance of this type of testing and for our country, especially for those people that cannot afford to do this type of testing on the outside centers. So I'm very grateful to have him and for his support. I really thank you for his support. And I think this would be end on my conversation, on my presentation. So if you have any questions, please do ask. Okay. Yeah.
So how cheap is it for people to do the test, the analysis?
Civilians that live here, actually it's free. But for people coming from outside, we get to the, we actually, the least it could be possible. I mean, the testing is the least amount. You know what I mean? It's free for the residents, but it's you have to pay a little bit money for the foreigners. But that's like, if it is double price on the outside centers at least. I can say that.
You mentioned about the
Yeah.
Is it available in your labs?
Well, we haven't started PGD yet because we haven't started, but that's the plan that we will be starting to do PGD in our laboratory, but it's on the process of actually announcing and then starting to do it. But we haven't started yet. But this has been actually started 2 weeks ago, so this is very new. So we're trying to all set it up, and but we're in near future we will. On painting, let's say, if there's different diseases on the whole chromosome, you can monitor. But it's like on a slide, you can put probes. So you can actually put 3 different probes on one slide. You know, you can put you can do 3 slides, and then you can check for 12 diseases. But in each area, you have to put specific probe to do it. If you want to analyze all, you have to do karyotyping, and that's sometimes actually wanted with the fish. So karyotypes is always good, but the thing about karyotype is like microdeletions or some submicroscopic deletions, you cannot able to see it because you can clearly see like any type of translocation if it happened, like 2 chromosomes actually change parts, or we can see if there's like trisomies and very clearly see in different the numerical changes, but it's sometimes hard to see very small differences. So that's we do fish. If you want to see all of them together, you have to do microarrays. That's available as well. And we do want to actually start doing this as well. So we want to actually, that's our next goal in the ministry, to actually buy a microarray device to actually do the molecular, again molecular level, to check the whole chromosomes together. And yeah. Okay. We are trying to get it bigger. We're actually trying to move to another place. So inside, we do take insurance. Actually, every summer we have like total of, we have to take them 2 by 2 so that it doesn't get too crowded. And now that there is a molecular part and cytogenetic part now, that and especially cytogenetic culturing of the cells, so that's very open to contamination. So we cannot like accept so many people at the same time, but we do. Yeah.
Is it priority also like for citizens or also for?
No, free of help to fill out an application, but you can come. You can come, and we really like students, so you're welcome to come. Yeah.
Is this open to the biomedical engineers as well for using the devices, or in genetic science?
Well, the priority, of course, is to genetics. From my vision, whoever is interested can come and to use our devices. They need to apply to the thing is, it has to be not crowded in the laboratory, and summer times are really crowded. So times around here, this time of the year, it's better. It's much better because it's hot. So everybody is actually lined up and waiting for an intern in the laboratory.